Hello everyone. In my last video, I discussed a 27 MHz crystal oscillator. The output power from that oscillator circuit was not much. It is very little power. So to amplify that power, we need an RF amplifier. In this video, I'll try to discuss a little about that. And our goal is to send the RF power to an antenna. So to do that, we need another circuit called impedance matching circuit. I'll also discuss a little bit about that. So as the entire circuit is built on a protoboard, this is not very ideal for a RF amplifier. So in future, I'll build the entire circuit on a printed circuit board and try to explain further. As my original goal is to send power wirelessly several meters away, at present, I cannot show that, but in future, certainly I'll do that. Previously, I discussed a crystal oscillator. Today, I am going to explain how we can amplify the signal and send the amplified power to an antenna. The crystal oscillator generates a signal at 27 MHz. So this will be the input to an RF amplifier. To amplify signal at 27 MHz, both bipolar junction transistor or a MOSFET can be used. However, presently suitable BJTs are not available in the market, as the manufacturers are more interested in making MOSFETs than BJTs. There are still some BJTs available, but these are expensive, especially if we are looking for a high frequency and high power transistors. So in this project, I am going to use a MOSFET to amplify 27 MHz signal. Now, to find a suitable MOSFET, we need to consider the gate capacitance of a MOSFET. If we take a look at the basic structure of the MOSFET, we can see the source of this gate capacitance, the metal plate, the insulation, and the conductive passage between the drain and the source. If the gate capacitance is high, the signal at the gate cannot modulate the conductivity of the channel between the drain and the source. So the lower the gate capacitance, the better the frequency response. I choose this MOSFET due to its low input capacitance. You can see the input capacitance. It is 115 picofarad. The only limitation of this MOSFET is this drain to source voltage, which is 25 volt. And sometimes we need a higher operating voltage for an amplifier. There are several classes of amplifiers: class A, class B, class C, and class D, E, F. Class A amplifier amplifies the whole signal. However, it is not efficient. A lot of power is wasted as heat in the transistor. Class B amplifies the signal in two sections. One section amplifies the positive half, and the other section amplifies the negative half. And these two parts are combined to get the whole signal. This is moderately efficient. The third type is called the class C. It amplifies only a portion of the positive or negative part of the signal. However, if this amplified portion of the signal is fed into a LC tuned circuit, we can get the whole signal due to the nature of the LC tuned circuit. The other classes of amplifiers mainly work as switches and are highly efficient. I am going to use the class C amplifier. for the RF amplification. The oscillator circuit that I built has an output impedance approximately 100 ohm. If this is fed into the gate of the MOSFET that I choose, the output signal will run from 7 volt to 12 volt. Due to the gate capacitance, the MOSFET output never goes to zero. This is not an efficient amplifier if the situation is like this. A toroidal transformer can be used between the oscillator and the MOSFET as a coupling device. The turns ratio could be 10 to 1, 10 to 2. This transformer will convert higher impedance into a lower impedance, which is then suitable to drive the MOSFET. Now the complete RF amplifier circuit is shown. A 3 microhenry inductor L1 is used to allow DC to the drain, but the RF output is blocked to the supply. So the RF is allowed to go through the capacitor C2 to the matching circuit and onto the antenna. So this is the photo of the practical oscillator and the RF amplifier circuit. You can see it is not built well. I need to use a PCB to make it work nicely. In future, I'll do that. For 27 MHz, ideal vertical length should be 2.65 meter. However, for test, I used a 1.2 meter long vertical antenna. The impedance is around 4.6 ohm. It has some complex part, plus or minus. I must match this impedance with the amplifier output to ensure efficient power delivery from the amplifier to the antenna. We want to feed the output of the amplifier to an antenna, and we have to consider various factors. First thing comes is the antenna impedance, and then we must match the antenna impedance with the amplifier output impedance. For matching, I use 2 coils L2, L3 and 2 capacitors C6 and C3, and C6 is adjustable. Using the various coils for L3, I use 3 different types of coils, and adjusting the capacitor C6, it is possible to match the impedance to some extent. For tuning, I used a simple field strength meter. It consists of 2 diodes, 1 capacitor, 1 small antenna, it could be a foot long, and a microammeter. These are the photos of the field strength meter. I used a multimeter with microampere setting. The small antenna should be located within the few feet of the other antenna, that is the transmitting antenna. By adjusting the capacitor of the amplifier and watching the meter, we can set the optimum tuning where the meter shows maximum deflection. These are the output waveforms of the amplifier. You can see not very good waveforms. In future, after building the PCB after building the circuit on a PCB, I hope to make this better. The video on the RF power transfer will come little later. I'll make some other videos in the meantime. I must look for a suitable power transistor for high power amp, as it will operate at 27 MHz, not that low frequency. I'll have to make it on a PCB, and I'll have to design a better impedance matching circuit, and finally a longer antenna. the amplifier circuit is shown here, and it is powered up, and small antenna is also connected. The length of this antenna is about 1.2 meter, and as you can see, there is a matching circuit, and it needs to be matched. And to observe the matching, I used a small field strength meter, and this is a field strength meter, and this antenna of the field strength meter is located close to the transmitting antenna. Now I am tuning. There are two capacitors, variable capacitors I need to tune, and when I see the maximum deflection on the meter, which means the tuning is nearly done. As you can see, the deflection change, and it is optimized now.